Welcome to step 10. By the time we're finished with step 10, you will be able to solve and graph inequalities with one variable. When we're graphing inequalities, you're probably familiar with the two symbols less than or greater than. You may have been taught that the alligator eats the bigger number, or to make it look like Pac-Man. I've always found that the simple fact that the less than symbol resembles a letter L is probably the easiest way to remember that this one is less than and the other one is greater than. When you have these symbols in your inequality, and remember, an inequality is just like an equation, but the two sides aren't equal, they are not equal, which makes them an inequality. If we have these symbols, when we graph it on a number line, we're going to use an open circle. Sometimes our inequality will be less than or equal to. That means we have the less than symbol and then we have half of an equal sign by underlining it, or greater than or equal to. When this happens, we're going to use a closed dot when graphing. Other than that, solving inequalities is just like solving an equation. You still try to isolate the variable by getting it all by itself on one side of the inequality. There's one special rule, though, that we have to remember, and this is important. You might even want to highlight it. You need to remember to flip or change the inequality sign when you multiply or divide by a negative number. This is a very important rule that's different. We didn't have to do that when we were solving equations because the symbol was an equal sign. Even if you flip an equal sign over, it's still going to look like the same symbol. But if you multiply or divide by a negative number during the process of solving, your less than symbol will turn into a greater than symbol, and vice versa. Let's practice a few examples to see how this will work. Again, I encourage you, especially when you're starting out, to put that imaginary red line down the center of your inequality. That way you can clearly see that there's a left side of the inequality and a right side. You can see that on the left side we have negative 2b plus 4, and on the right side we have negative 6. Now we're going to proceed to solve for the letter b just like we would if this was an equation. We're going to subtract 4 from both sides. Which leaves us with 2b is greater than negative 10. Now I know you see this negative symbol, but nothing has been multiplied or divided yet, so everything is fine with our original inequality symbol. We're still trying to isolate the b. In order to get rid of this negative 2, we need to divide by negative 2 on both sides. This is where you need to be careful of your symbol. By dividing by a negative 2, we must flip our symbol from greater than to make it less than. On the left, the negative 2's cancel, and we just have b. And on the right, negative 10 divided by negative 2 would simplify to 5. Finally, we need to graph this. So I'm going to stretch out a number line. I'm going to put 0 in the center. You don't need to label every single mark on your number line, just a few. So here's 5. Going the other direction, you could call this negative 1, 2, 3, 4, negative 5. Just have a few numbers on your number line so you understand where we are in the graph. Because this is a strictly less than symbol, I'm going to put an open dot on 5. And when your letter is on the left, when the variable is on the left side of the inequality, this symbol will match the symbol that you want to shade towards. So we want to actually shade to the left because that's where B is less than 5 on our number line. Sometimes people shade by making a squiggly line on top of it. Other times people prefer to do a number line that looks something like this. Let's see where we put our 0, 5, -5. We could put an open dot and then highlight. That's acceptable as well. You just want to indicate that this part of the line, less than 5, is our solution. Let's try another one. First, I'm going to put my imaginary red line down the center. Try that again. Kind of got a little squirrely. All right. The first thing to do when we solve is to subtract 15 on both sides. 3x is less than or equal to 6. Then I'm going to divide by 3. The 3's cancel. I don't need to flip my symbol this time or change it to greater than because 3 is positive. 6 divided by 3 is 2. This is my solution. And now I'm going to graph it. I sketch a number line, put 0 at the center. Here's 2. -5 would be down here. +5 would be up here. I'm going to put a closed dot this time on 2 because it is less than or equal to. And I'm still going to shade where the arrow matches my symbol because my variable is on the left. When the letter's on the left, you can shade the symbol to match the arrow. And then I will shade my number line, make a little squiggle so that it doesn't accidentally erase. And there's my solution. The third example. Step 1, we add 1 to both sides. I'm left with d over 2 is greater than or equal to 4. To get rid of divided by 2, I need to multiply both sides by 2. Should I flip my symbol? No, I'm not multiplying or dividing by a negative. So d is greater than or equal to 8 is my solution. I sketch a number line, 0 at the center. I'm going to graph 8, +8, which would be right here with a closed dot. And I want to shade the arrow that matches my greater than symbol, which is right here. So I'm only shading a very small part of my graph. For number 4, it says, let's define a variable and write an inequality and solve. I'm going to let x be my variable, but you could have used any letter. And again, this takes us back kind of to step 6 when we were translating language into mathematics. 4 more than the quotient of a number and 3, and this is where it'll get a little tricky, is at least 9. Starts off pretty straightforward. 4 more than the quotient of means I'm going to be dividing a number, which we said was x, and 3 is at least. What are we going to put for is at least? Well, think about it. If I tell you I have at least $9, could I have $9? Yes. Could I have more than $9? Absolutely. Could I have $7? No. So I have at least 9. That means I have 9 or more. So we're going to write greater than or equal to. That's the symbol we're going to use whenever we see the words is at least 9. And now we're going to solve. Going to rewrite this off to the side so I have a little bit more space. 4 plus the quotient of a number and 3 is at least 9. I'm going to subtract 4 to start with. Then I'm going to multiply by 3 on both sides. X is greater than or equal to 15. And that's my answer. What would that look like on a number line? If I put 0 at the center. Again, I don't want to count by ones, or I probably have to make my tick marks a little bit too close. I think I'll count by 5s. 5, 10, 15, 20, 25. 5, 10, 15, 20, 25, 30, all the way down to negative 35 here. I'm going to put a closed dot on 15, and I'm going to shade my symbol that matches the arrow. Rather, shade the arrow that matches the symbol. I think I said that in reverse. And connect. Sometimes we're going to have what's called a compound inequality. A compound inequality is two separate inequalities that are connected with the words and or the word or. When you see that, you're going to actually have either two pieces shaded, particularly if it says or one piece shaded that doesn't go on indefinitely to the left or to the right. It's going to be contained in the center of our graph, of our line. Let's graph b greater than 3. Let's start with that. B greater than 3 tells me to put an open dot on 3. And if I want to shade, I want to shade where the arrow is pointing to the right. Next, I'm going to graph b less than or equal to 0. I'm going to change colors just so that you can see the two pieces. So this was the blue part of my shading. This will be the red part. I'm going to put a closed dot on 0, and I'm going to shade to the left this time where the arrow points to the left. So I actually have two pieces of my graph shaded now. Let's try the next one. We're going to put a closed dot where z equals 3, and it says shade to the left. Then we're going to put a closed dot on -2 and shade to the right. But notice this one says and, but the original said or. Can I stand on the red part of the line or the blue part of the line? Yes. Down here, if I need to stand on the red part of the line and the blue part of the line, I need to eliminate some parts of it. I only want the parts that are red and blue. So I only shade the parts in between these two numbers, in between -2 and 3. That's my final answer. Let's go backwards. Let's write a compound inequality for this graph. Whenever you have the shading in between 2 points, we can simply write the numbers and put the x in between them. -3 is smaller than x, which is smaller than 3. -3 is less than x, is less than 3. Now notice I have a mistake. There is a closed dot on +3, but we have an open dot on -3. So I actually want that one to be strictly less than. For this one, I'm going to have 2 pieces, so I'm going to use or. I'm going to have a piece right here on the left side and a piece on the right side. The left side piece is created with the -2, and it's shaded left, so I put a less than. The right side piece is created starting at 1, and it shades to the right. Pause the video and try numbers 9 and 10 and see if you get the same answer as me. Did you get these same answers for 9 and 10? If you didn't, be sure to ask your teacher in class to see what you might be doing wrong. Let's solve some compound inequalities. They're not difficult, it's just like doing 2 problems on the same graph. I'm going to just break it down into 2 sides. I have an inequality on the left, and I have an inequality on the right. We're going to solve them separately, then graph them. On the left side, I'm going to subtract 3. So I have the m is greater than or equal to 2. On the right side, I'm going to subtract 3. And I have m is less than 4. So to write my answer, I could put them together with the word and. I would say m is greater than or equal to 2 and m is less than 4. Let's put these on the number line. Starting with the first inequality, I'm putting a closed dot on 2, and I shade greater than where the arrow points to the right. For my second equation, inequality, I'm going to put a closed dot on 4 and shade to the left. But remember, it says and, so I need to be on the common part, which is right in between these two numbers, and I can erase the rest of it. The only way I can be greater than or equal to 2 and less than 4 is if I'm right here in the middle. I made a silly error again. That needs to be an open dot on 4 because it's strictly less than. Number 12. Let's solve each inequality. The inequality on the left, I'm going to add 5. So I get y is less than 1. On the right side, I'm going to also add 5 for this equation, this inequality. I get y is greater than or equal to 6. And I'll put the word or in between them. This is my solution. Let's graph this. At 1, I'm going to put an open dot and shade to the left because my variable is on the left, so I match up the symbol with the arrow that matches. For the other piece, I'm putting a closed dot on 6 and I'm shading pointing to the right, greater than. That's my solution. Pause the video and try 13 and 14, then check your answers. How did it go? Did you get the same answers? Notice that on the first problem, number 13, we were left with the variable on the right side. That's not wrong to leave it like that. However, when it comes to shading, it's best to have your variable on the left side. So if I flip this inequality over, f will be on the left, -2 will now be on the right, but by flipping them, the inequality symbol flips. Notice right here, 2 points of the inequality symbol are facing f. So when I flip my symbol around, it still needs to be facing the f. Once I do that, I can use that line to shade my number line. We have just 2 more problems for our notes today. We're translating again. A number decreased by 2 is at most 4 or at least 9. So let's begin translating. A number, we'll call it x, decreased by 2 is at most. When you see is at most, think about what happened earlier when we had is at least. Is at least means greater than or equal to. Is at most means less than or equal to. And again, think about it with money or objects. If I have at most $4, I might have $4, or I might have 3 or 2 or 1, but I can't have 5. It has to be less than 4. Less than or equal to 4. Or at least, which means greater than, or equal to 9. Now we're almost finished. I've translated each piece that I highlighted. However, we can't just have one inequality and then a half of an inequality. So whatever I've written on the left here would also go in the inequality on the right. A number decreased by 2 is at least 9. Or a number decreased by 2 is at most 4. Now we're ready to solve. When I solve the inequality on the left, I have x is less than or equal to 6. When I solve the inequality on the right by adding 2, I have x is greater than or equal to 11. And when I graph that on a number line with 0 at the center, I will put a closed dot on 6 and shade to the left, and I'll put a closed dot on 11 and shade to the right. Our last problem, the sum of a number and 3 is no more than 8 or is more than 12. So translating on the left, we have the sum, which means add, a number and 3 is no more than 8. So let's think about this. Can it be greater than 8? No, because it says no more than. Can it equal 8? Yes. Or be less than or equal to 8. Or, now I'm going to take this first part again, the sum of a number and 3 is more than 12.